Okay, let's get started with Chapter 2. So I know that our Chapter 2 started off with all of this information about Dalton. The biggest takeaway that you need to know is that there are a few laws on this page. One of the laws is that there's a law of definite proportions and there's a law of multiple proportions. The last law is the law of conservation of matter. That was actually in the last chapter, but I'm bringing it up here so that all the laws are together. This basically means that you cannot just lose matter. So matter can be transformed, but it doesn't just like stop existing. The law of definite proportions only applies to something that's pure. And it's just saying, like, if you get a little bit of a sample of something pure, so if I got this, and if I just pull out, like, this little tiny bit of it, the ratio of that is going to be the same as if I pull out, like, a huge section of it. So we're not saying that they're going to weigh the same, but we're going to say that if something is pure, like pure NaCl, let's say, so if something is pure and it has all NaCl's in it, this little sample will always show that the Na to Cl ratio is 1:1. And this sample, even though there's more of them in there, it's still the same ratio of NaCl being 1:1. Or whatever other compound that you can consider. And then the law of multiple proportions, this has to do with how elements combine. So we're not talking about pure compounds anymore. We're not talking about something pure. So we got like some kind of mixture thing going on. And we're talking about that they still combine in certain ratios, specific ratios. But in some cases, like in one compound, like for example, CO, the ratio is 1:1, whereas like in CO2, the ratio is 1:2. So some of this might make sense when you're just looking at it and you're like, yeah, obviously there's one of those and one of those versus one of those and two of those. But the law of multiple proportions, it's just saying that like when you combine, you have to combine with a whole oxygen, not like half of an oxygen. And it's a multiple of oxygens is what you're going to end up with. So you can have CO, CO2, but you can't have CO 1.5 kind of a thing. All right, so those are all laws. And that's about all that you need to be worrying about on the page. Now, it does say to explain the historical development of atomic theory and identify some scientists who made the contributions. So here are the four main scientists that we talked about, and I kind of made a big deal that this time I just really want to make sure that everyone is aware of Rutherford because he came up with some really big ideas. He said that the proton exists, that the nucleus is a positive charge, and the atom is mostly empty space. So on a football field, if you have a grape in the center of the football field, that's the nucleus, and the atoms or the electron is way over on that 1 yard line, and the electron's only 1,000th of the size of the proton. And he used the gold foil experiment to learn about how this worked. All right, so when we're talking about differentiating between electrons, protons, and neutrons, you're probably at the point where you already kind of get this. But a nucleus, that's where your electrons and protons are. So you can see we've got them in here. Your protons, your neutrons. They are in the nucleus right here. And then the electrons are the little tiny things that are on the outside. And just remember that these pictures that are drawn here aren't really great pictures. Like it's more like this. Like it's really, really far away. And don't forget that it's 3D space that we're talking about, not like a flat surface. And this is a big deal in chemistry, is understanding what this picture means right here. So in class, I didn't specify, but the A is your mass number and the Z is the atomic number. So A is earlier in the alphabet, it's higher. I don't know if that helps or not. So one of these numbers, so we got like these whole numbers on here. One of them is on the periodic chart, and it's this guy right here. So we've got him circled. He is on the periodic chart, but the other two numbers aren't. So the atomic thing is on the periodic chart. This other number that's on the periodic chart over here, this is not any of the numbers that we're talking about at the top of the page. This is going to be the thing that you calculate, and it's the atomic mass, and it's not just any atomic mass, it's the percent abundant or it takes into consideration the percent abundance of all of the masses of all the naturally occurring isotopes. Some people will call it the weighted average atomic mass. But in all honesty, we also will shortcut it and just call it atomic mass. So what are these other numbers that are not on the periodic chart? Well, some of these numbers, they have to be there. If we ask you questions, you're going to need numbers in all three of these different positions. So we're going to look over here at the mass number. So this right here, this 4 is the mass number, and that's the number of protons and neutrons. And you'll notice that the mass number is always bigger or equal to the atomic number. And it's kind of nicely arranged so that you can really easily do the math. 4 minus 2 gives you 2 neutrons. So it's all nice and neat. The other thing on this chart is that we have the charge over here. And so the charge is the protons, the number of protons minus the number of electrons. So if something is neutral, your number of protons and your electrons are the same, and you would not have anything here. So if there's nothing in this position, so if there's nothing, we don't usually put a 0. That means 0. But if there's something here, it's going to be like 2 plus, 1 minus, 3 plus, 5, 7. You know, it's going to have a number and then also a plus. And so, for example, on this one, the charge is plus 2, and you had 2 protons, and there were 2 electrons. So we're subtracting because we're trying to get the E by himself. So we're subtracting this 2 out right there. So we get that 0 is equal to your negative E. And so, again, if you divide by a -1, you still have E. So this one does not have any electrons. And that makes sense because he had 2 protons and 2 electrons to start with. And he keeps losing electrons. It's going to become more and more positive because you're losing what's negative. So he's lost those two electrons. You need to be able to do this for any kind of element that has any kind of a charge and any kind of arrangement. That's a very important thing that you have got to be able to do. And also related to that is if you had like a whole series, like in this example right here, you've got to be able to get to all of the different numbers of subatomic particles. And the question might be a multiple choice question where like this is A and this is B, and they want to know, hey, which is the answer that has 15 neutrons? So you're going to have to go through this work and figure out, oh, that's got 14, that's got 16, oh, that's the one that has 15. And you probably should check the last one to make sure that you haven't messed up. Or another one might say, which one of them has 15 protons? Well, he has 15 protons and he has 15 protons. So that wouldn't be a good question, right? And this is just kind of a level 2 problem. I definitely would make sure that you know how to work these kinds of problems. And there was an error in this one. This was supposed to be TH plus 4. So I'm correcting that right now. If you have questions on this, feel free to come and ask. But you've got to be able to work through all of those. Also, if you were given a chart like this as a question, and maybe there was a blank spot and this was like answer choice A, and this was answer choice B, and this was answer choice C, you know, you need to be able to, or they ask you to find one of those, like maybe maybe there is nothing here, they want you to find what A is, then you have to be able to fill it out and break it apart. It's the same idea for everything, though. The idea is that you've got to find your protons, which is the bottom number, subtract from the top number to get your neutrons, and then if you have a charge like here or here, then it's the protons minus the electrons. So just to be really, really clear, we do call this top number a mass number, and I see the word mass is in it. And then we also have over here an atomic mass. So make sure you're very clear that they are not the same thing. A mass number, so both of the things that are numbers are whole numbers. The atomic mass is what comes from the periodic chart, and it's a weighted average. Just make sure you're very clear. That's a fantastic question to ask, something like that. Speaking of the average atomic mass, you need to make sure that you can solve at least a not too complicated version of the atomic mass average. So here's an example of an atomic mass average question. Calculate the atomic average of this element. So we have a percent abundance right here, and we have a mass. And notice like these are in the same sentence. There's the word and. They're like connected to each other. That's why we drew that line. And then over here, 0.26 abundance, and here's the mass. And so again, they're connected to each other. And then last but not least, we got these two guys, and they're connected to each other. So all you do is you're turning this percentage right here into a decimal by dividing it by 100. So you're just turning that in 9.92. So you're used to doing that. And this guy, it's going to become 0.0026. And this guy, again, we're just turning him into a decimal. And once we get in the decimal, we're just multiplying by the weight that he's paired with, or the mass that he's paired with. So it's just the 0.9092 times the 19.99 plus this number times him plus this number times him. Or you can just put it all in your calculator all at once. The answer is the average atomic mass. And your average atomic mass is also going to be generally close to the most abundant isotope. And you wouldn't be asked a question where it's questionable. It's going to be very clear. So the most abundant isotope of this is going to have a 20 up into the top of it. And you can also use this to figure out what the element is. So if you look at the periodic chart, if you bring out a periodic chart, there's only a few that are around 20. Neon is 20.1. On my chart, he's 20.18, but that's very, very close. The next closest is 22.98, which is sodium, and fluorine was less. It was 18.99. So the only one that's anywhere close to this is neon. So you can use that to figure out an unknown. So this would be 20 neon would be the most abundant, and we're not saying that there aren't others, because there are. But the most abundant one would be 20 neon. And remember, I just look at the periodic chart, and I've got a 10 beside the neon to figure out how many protons. I just look at the chart. It's the only number in the chart that's not a decimal. It doesn't say anything in here about it having a charge, so I'm not going to worry about anything in that position. So we just leave that blank. So you need to be able to do that. And I wanted to point out something in this problem right here. This problem is worked on the internet. You can Google and find versions of this one. But I want to point out, if something is composed of two isotopes and only two isotopes, and if you know that one of them is this percentage, can you figure out the percentage of the other one without having to go through all the math? You can, because they both add up to 100. So it's just 100 minus 19.9. This is what the other percentage is going to be. So this works if there are two isotopes and you know one of the two percentages. It would work if you had three isotopes and you knew two of the percentages. So that's a great shortcut for a problem like this. So definitely keep that in mind for the test. All right, so now there's just a little bit more. And this is something that is very short. And you do need to know the difference between this formula right here. So this is just the formula. We call it the molecular formula. Molecular formula. This is the structural formula, and you really, honestly, on our learning objectives, you need to know this one, and you need to know this one. And then you also need to know the difference between something that's empirical and molecular, and the empirical is the easy one, and it's the lowest ratio of atoms. So notice this is like 1 to 4. versus this is 2 to 8, 3 to 12. Those are higher ratios. And again, that's the empirical one right there. It's 1 to 2 versus these other ones are higher ratios. So just make sure that you know the difference between empirical and molecular formulas. Now, the last bit of math that's in this section, and again, there's a lot of videos to help you with this if you are struggling. I'm going to go ahead and jump to a problem for some examples. So right here, how many moles of water are present in 1.50 grams of sample? There's only one number. You're starting with a gram right here. There's your gram. And just like all the other factor conversions, you put your gram on the bottom and you're going to convert it up into a mole because that is a relationship that we know. And this comes directly from the periodic chart. So this is on the periodic chart. This is hydrogen's number, and this is on the periodic chart, and that's oxygen's number. I need 2 of them because there's a 2 right here. You add them up. That's going to give me my number that goes beside the grams, and every single square on that periodic chart, it represents 1 total gram. I'm sorry, I meant to say 1 total mole. It represents 1 total mole. Every square represents 1 total mole. And that's why we have a 1 right here. At this point in chemistry, most of the time, we're talking about 1 mole of something when we're talking about conversions. That will change in Chapter 7, but for now, if you're getting a number off the periodic chart, the 1 goes beside the mole. And here's a longer example. So right here, the number of atoms of carbon. Again, you're going to put atoms on the bottom, and then you're converting it into moles. So this example is using Avogadro's number. And anytime you got Avogadro, it's 1 mole is equal to 6.022 times 10 to the 23rd atoms. So if the 1 mole needs to go on the bottom, it would go on the bottom, and you can put this number on the top. Or likewise, if you need the 1 mole on top, you can put this number on the bottom. We use the word atoms because we are talking about carbon and because the question says carbon atoms. Now notice this one says molecules of NH3, but a molecule is the smallest you can get and still be NH3. If we were talking about atoms, then we'd have to like say, oh, I'm talking about 1 nitrogen or 3 hydrogens. We would have to break it up and it would no longer be ammonia. So a molecule is the smallest you can be. And so in this case, we're going to take our grams. So here's our grams right here. We're going to convert it into moles. And then again, our moles are going to be canceling. And then we're going to convert it into molecules. And it's molecules because NH3, the smallest unit of NH3 is a molecule. Notice that these are both nonmetals that are bonded. That's one reason that we call them molecules. Molecules are, they have subcategories. So everything that has more than 1 atom is a molecule, but you've got your molecule and you've got your compounds. So a compound is like a subcategory of molecule. These are going to be, if you're talking about it like this level, this is going to be a nonmetal and a metal. And the compound, it's just a nonmetal, and the compound is going to be a nonmetal and a metal. So a compound is a type of molecule, but you can have molecules that are not compounds. We use a formula unit when we're talking about compounds. We had a lab about that. And there are a lot of problems that are worked out for you. This problem right here and this problem is kind of a fancy twist. You want to make sure that you understand it. We've got 1 gram of H2O2, so we've got that. That's the only number we've got. This right here is what we get when you add from the periodic chart. But the question wants to know about oxygen atoms, not hydrogen peroxide. It's asking about oxygen atoms. I can't jump right to oxygen atoms. I've got to get to moles before I can talk about oxygen. And the reason that we have moles of H2O, the reason we have a little 2 right here and we have this 2 up here is because there are 2 oxygens in 1 mole of H2O. And we always just assume 1 mole. It's the easiest. If I were to say 2 moles, then I would have to use a 4 up on top, and that's a lot more complicated. So just assume, when you're trying to go like within a molecule, assume 1 molecule, or 1 mole. Then once we're in moles of oxygen, we can go on and go into grams. And so this has us just being at oxygen atoms. And then this bottom problem, what this does is this gives you density. So you'd probably be thinking, oh no, density. But whenever you get something that has that divided by symbol, that's the same thing as writing 0.789 grams is equal to 1 milliliter. And the 1 is understood because you can always divide any number by 1. So it's a hidden way of saying, oh, this is really a conversion factor. Whenever you do these problems, don't start with a thing that has 2 units if you don't have to. So that has a gram and a milliliter. Don't use that one. Use this one. It's got 1 unit. So start with 1 unit. So we've got this number, and that's our moles of carbon. Immediately write the moles of carbon on the bottom. Now, for moles of carbon, you could go to 3 places. You could go to atoms, using the Avogadro's number. This one is not asking you about atoms. You could also go to grams, and that's from the periodic chart. Or you could go to like a bigger molecule, which is what we're going to do right here. The other, it's asking us about ethanol. So our final answer needs to be about ethanol, not carbon. Our final answer needs to be about ethanol, and this is ethanol, C2H6O. You would be given a formula. You would not be expected to know what ethanol is. So we're going to go, we don't need to go into atoms because it doesn't ask about the atoms. It's not asking us about the mass of anything. It's asking about milliliters. So we're going to go from carbon atoms, moles of carbon atoms, to moles of, and this is your ethanol right here. And notice that there are 2 of these here. That's why it's good to write the moles, the units out, and then go back and put the numbers in so that you can see them. Now we're in ethanol, so this is great. So now we're talking about ethanol. Moles into grams. Now at this point, I can't use the conversion over here yet because I'm not at grams. Right here, I'm just at moles. I've got to get 2 grams. And again, this is from the periodic chart. That's just adding it all up. And now we have grams, and you can put a gram on the bottom and turn it into a milliliter. So this would be like probably one of the higher level problems that you'd have to be able to do if you can do this one. And I'm not saying that you have to be able to, but if you can do this, this is kind of the cream of the crop. If you can do this, then you pretty much understand what all is going on, and you're in a good place. And that's the end of the chapter 2 stuff.